our Taylor series problem. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. And it's known that f of 1 equals 1, f prime of 1 equals negative 1/2, and the nth derivative is going to be given by this expression. So I need to write the first 4 non-zero terms and a general term of this Taylor series. So my Taylor series, remember that this is supposed to be the sum of the nth derivative at a times x minus a to the n over n factorial as n goes from 0 without bound. So for our purposes, I'm going to start with this value. This is where n equals 0. So this is going to be 1. This is where n equals 1. So this is going to be negative 1/2 x minus 1 to the first over 1 factorial. And I'm going to be using this for my higher order derivative. So my second derivative is going to be negative 1 squared times 2 minus 1 factorial over 2 to the second power, or 1 times 1 over 4. So this is going to be positive 1/4 x minus 2, 1 squared over 2 factorial. And I need to do the same thing for my third derivative, which is going to be negative 1 cubed times 3 minus 1 factorial over 2 cubed, which is going to be negative 1 times 2 factorial over 2 cubed, or negative 1/4. This is going to be x minus 1 cubed over 3 factorial, plus now I need to write my general term. And remember, it's going to be my nth derivative at a, which is going to be negative 1 to the n minus 1 factorial, over 2 to the n, times x minus 1 to the n, all over n factorial. And I don't have to simplify this. I can leave this like this. That's fine. So that's going to be my answer. Moving on to part B, says the Taylor series f about x equals 1 has a radius of convergence of 2. A radius of convergence of 2 means I'm going 2 units to the left and 2 units to the right. So I know that I'm going to be between negative 1 and 3. But if I'm looking for the interval of convergence, I need to know, do I have equality here or do I not? That's the question here. So I need to check the convergence at these endpoints. So the first thing I'm going to do is check for convergence at x equals negative 1. So for our purposes, when x equals negative 1, remember that our generic term was negative 1 to the n. And this is going to be x is, actually let's go back here and get this formula real quick. So we've got this negative 1 to the n minus 1 squared factorial over 2 to the n, x minus 1 to the n over n factorial. So substituting everything I've got, looking for the limit as n approaches infinity. I've got negative 1 to the n minus 1 factorial over, I have an n factorial in the denominator, and I have a 2 to the n in the denominator as well. N factorial 2 to the n, 2 to the n, times x minus 1 to the n. So for this, that's going to be negative 1 minus 1 to the n. So what I've really got here is I've got the limit as n increases without bounds of negative 1 to the n times, I've got n minus 1 factorial over n factorial, so I'm going to have just an n in the denominator. In the numerator, I still have a negative 2 to the n over 2 to the n. And the problem that I have is that this negative 1 to the n and this negative 2 to the n really give me a 2 to the n over 2 to the n with this n. And if I let my 2 to the n's go away, I notice that I've got a harmonic series, which diverges. And so the question is, are we less than or equal? We are strictly less than. But I need to do the same check for x equals 3 and see what happens. So I'm looking for the limit as n increases without bounds of negative 1 to the n minus 1 factorial over n factorial times 2 to the n over, this is going to be 3 minus 1 to the n. So looking at the simplification that we've got that negative 1 to the n I've got just an n left because this n minus 1 and n factorial leaves just an n here. And then I've got 2 to the n in the numerator and 2 to the n in the denominator, so I've got the limit as n approaches infinity of negative 1 to the n over n, which is an alternating series test because this is our alternating harmonic. So we actually do have equality here. So our interval of convergence is going to be negative 1 strictly less than x, less than or equal to 3. All right, and part C says the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So if I'm looking at this to approximate this, I need to say that f of 1.2 is going to approximately be equal to what happens when I substitute into the first 3 terms. That, remember, the first term was 1. The second term was that 1/2 x minus 1 to the first over 1 factorial. And the third term was that 1/4 1.2 minus 1 squared over 2 factorial. And of course, I can leave my answer just like this. I don't have to simplify this. That's beautiful. All I've done is I've just substituted 1.2 into the answer that we got on part A. So all I've done is I've substituted here and here. And I only needed the first 3 terms. And the reason you'll see is going to be explained on part D. Part D says show that the approximation found in part C is within 0.001 of the exact value of 1.2. And remember that our error bound says that our error has to be less than the absolute value of the next term. So for us, that next term is going to be negative 1/4 times x minus 1 cubed over 3 factorial. So for us, that's going to be 1/24 of 0.2 cubed. So it's really going to be 0.008, that's 0.2 cubed, over 24. And 8 goes into 24 3 times. So this is really 0.001 over 3, or 0.0003 repeating, which we agree is all less than 0.001. So I'm using the error bound. This error bound comes from the alternating series. Whenever I have an alternating series, this is going to be true. And 1.2 definitely is in the interval of convergence. So 1.2 is in the interval of convergence, which we found before to be from negative 1 to 3. So because we're in the interval of convergence, this error bound holds, and the error find from that subsequent term is indeed less than 0.001. And that's our AP exam. So for everyone